So let's go through FLIM now. So as I mentioned, independent of the spectrum or the wavelengths that are generated from the emission from your molecules, the fluorescence lifetime can be very different. So for example, AF488 and E-enhanced GFP, which have very, very similar spectral characteristics, you wouldn't be able to separate those on a standard confocal, have very, very different fluorescence lifetimes, which would allow you to actually separate that out. So some experiments you can use it for are FRET applications, things like multispectral analysis, or even just autofluorescence imaging as well. So this is autofluorescence within a plant tissue. In terms of analysis of FLIM data, one of the ways that people do this is using something called a phasor plot. And essentially you can look at the lifetime of the fluorophore on this universal circle. In this case, you don't have any frets, so the lifetime is much longer, whereas as you increase your frets, then the fret signal increases. So this is again a biosensor which is used looking at histone binding, again from the university group at the University of Melbourne. Okay, let's move on to super resolution microscopy. So as I mentioned before, we have the diffraction limit, which limits us to about 215 nanometers in resolution. That means to see two objects as two objects, they need to be more than 250 nanometers apart. That's obviously quite a large limitation if you're doing super resolution microscopy. So there are a number of super resolution techniques which have been developed to get beyond that diffraction limit, some of which are on this table here. I won't go through the table in detail. Okay, so one that we use quite a lot within our platform is a confocal super resolution method, which is called the ARIScan detector. This is available on most of our Zeiss systems within the BOMP platform. And it works on the understanding that if you narrow down your pinhole on the system, you can actually increase your resolution. So you see here, as your pinhole decreases, your resolution increases. The reason that most people don't do that is that by narrowing down your pinhole, you're actually blocking 95% of the light that comes through to your detector. So in this case, you would normally have a pinhole at what we call 1 area unit. And we'll discuss that on Thursday in terms of what that means. But this essentially can be your detector. So we're detecting at 1 AU. What the ARIScan detector does is it actually has an array, again, of 32 individual detectors. And that means that each subunit detector has an effective size of 0.2 of an area unit, which essentially gives you that increased resolution. With a bit of clever mathematics, we can put this back together, and that will give us a 1.7 to 2-fold increase in resolution in all 3 directions. So this is an example of the same field of view imaged in confocal mode versus ARIScan mode. We can go a little bit beyond that. So with a bit of post-processing, so with ARIScan processing, you can get down to about 120 nanometer resolution. That's this example here on the top. If we go through the Huygens ARIScan deconvolution package, we can get that down to 90 nanometer resolution, and that's the example here on the bottom. So with a bit of post-processing and correct acquisition, we can really push down into much higher levels of resolution. Structured elimination is also one of the common super res techniques that's used. The nice thing here is that it's camera-based. And you don't have to change any of your fluorophores, so you can image GFP, you can image antibodies. That gives a 2-fold increase in resolution in all 3 directions, which is an 8-fold increase in volume resolution. up to 4-color imaging. And what we're doing is that we're actually illuminating our sample with this grid pattern or with a lattice shape more recently. And this creates something called a moire pattern across our sample, which we can mathematically extract super resolution information from. There's a lot of, again, post-acquisition processing to increase the resolution. The downside is you're taking a lot more exposures than your confocal. So again, isn't always applicable to live cell setups or samples which are fairly faint, but can produce some really nice data. So this is wide field image versus 3D sim image of some Hendra viruses. This is a malaria parasite, again, wide field versus sim. And then a eukaryotic cell stained with HeLa in wide field and sim modes. The final super res method that I'm going to talk about, I can get this movie to play, just take the laser pointer off, is single molecule localization microscopy. So there's a number of different ways of doing this. They all work on the same principle that you don't want, as we have in most fluorescence, all of your molecules to be fluorescing at the same time. You want only a few to be emitted at any one time. So in the PALM method, we use specialist fluorescent proteins to be able to do this. In STORM, we use high-powered lasers and a bit of chemistry to make most of the fluorophores be in a long-lived off state, and only a few will emit at any one time. In DNA paint, we're using the binding of an oligo to a complementary sequence on an antibody to kind of produce that blinking pattern. So this is a very macro scale example of super resolution microscopy. This is the Eiffel Tower, and this is a video of it at night. It blinks, and what we're doing here is detecting individual, essentially, fluorophore emissions, marking that, producing a Gaussian fit, and then plotting that with a much, much higher resolution. And then over thousands and thousands of frames, we can build up this super resolution image. Okay, and this can produce this type of image here. So again, this is the malaria parasite, again, imaged in wide field on the left versus single molecule imaging on the right-hand side. And these little horseshoe donut shapes, they're about 100 nanometers across. These single molecule methods will get you down to about 20 nanometers resolution. Okay, so that's the overview of where we've been. So we've covered all the way from large pieces of tissue and model organisms all the way down to single molecules using light microscopy approaches. Hopefully some of those will be applicable to you in your research.